All right. So for CCDP and module number 1, which is what we call the Enterprise Connectivity and High Availability module, obviously in this particular, that's a really generic description of the module, but what we're going to talk about in this module is essentially 3 different topics. We're going to talk about designing EIGRP routing, designing OSPF routing, and designing ISIS routing. Now, we may not spend as much time on ISIS, but we will certainly spend a lot of time on EIGRP as well as OSPF and ISIS. So in the first lesson, we will be talking about EIGRP. Now, there may be, obviously EIGRP is covered quite heavily in the CCNP course, as well as CCNA routing and switching. So everybody's fairly familiar with EIGRP, but I'm going to make the assumption that maybe perhaps, maybe a little rusty, maybe you haven't had a chance to implement as much EIGRP as you might have had an opportunity to implement OSPF and so on. So what we'll be doing is kind of filling in some of the gaps as well as we go through the course, and I'll be doing some demonstrations and whatnot. When we're implementing EIGRP, obviously the goal of implementing any kind of routing protocol is optimization, efficiency, performance, scalability, etc., right? So what we're going to talk about in this lesson is how to design a multi-layer EIGRP topology, how to look at different design concepts, look at what we call these things called design zones, take a look at choke points in an EIGRP design. We'll take a look at implementing summarization, of course, and some of the caveats to summarization, some of the things that you have to be aware of if you're dealing with summarization. And then we'll look at EIGRP hub and spoke topologies and implementing EIGRP in a DMVPN cloud or a DMVPN network. All right? So there are several things, obviously, when we talk about designing or implementing EIGRP that we have to take into consideration. What is one of those things? Well, how do we make sure that EIGRP converges quickly, right? And what are some of the tools that you remember or that you're aware of that allow for EIGRP to converge more quickly? Any ideas?
Feasible success.
Right. Designing in feasibility condition, performing that algorithm check for making sure that we have a backup path. Query scoping is another concept that we talk about. We're using stub routing features in EIGRP. And then we also take a look at summarization, right? Those are really the 3 main components to really achieving that fast convergence in EIGRP. We'll talk about what do we do if we have multiple autonomous systems. The reason for having multiple autonomous systems, generally EIGRP is a very flat network, right? Unlike OSPF, where we have this hierarchical design and we have multiple OSPF layers, right? You've got your backbone and then you've got your non-backbone areas. In EIGRP, we don't really have that concept, right? So we have to work with multiple EIGRP autonomous systems in order to kind of achieve a similar design. Bidirectional forwarding detection is another component that we'll talk about that we didn't really see in the CCNP class. We'll talk about EIGRP Graceful Restart, NSF, nonstop forwarding fundamentals within EIGRP, the hierarchical design of EIGRP, where we can see different choke points in the EIGRP design, the 2-layer hierarchy for EIGRP, the 3-layer hierarchy. So you can kind of get the idea. We're really going to be talking about a lot of the key design elements of EIGRP. In CCNP, you learn the fundamentals, right? What is the algorithm? How does the algorithm work? What is a successor? What is a feasible successor? What is a feasibility condition? What is a reported distance, etc.? But obviously, we don't really talk about in as much detail the design elements of EIGRP. We know what a query is. We know how we can, what stub routing features are in EIGRP and so on. But we don't necessarily know all these other design components that we'll talk about. And I think you'll get a lot out of that when we talk about that in this class, in this particular section. In addition, we'll talk about the concepts of hub and spoke design and what is the effect of hub and spoke design in EIGRP. How can summarization lead to black holes, right? We know that when we create a summary route in any instance, whether it's a static summary route or OSPF or EIGRP, there's a null zero route that gets created. That null zero route could actually create black holes. So we have to be able to, we have to be concerned about that. Suboptimal routing is also another concern. Stub routing and stub leaking. Stub leaking is another concept that we didn't typically talk about when we talked about EIGRP in the CCMP class, right? And then DMVPN, right? In the CCMP class, we don't spend a lot of time talking about DMVPN either, right? There's an introduction to it, and there's some basic DMVPN discussion, but not in as much detail as we would see in this class. So that's really what we're going to be looking at in this particular chapter. All right. Welcome, Fernando. Glad to see you made it. You haven't missed much. We just basically started. We're waiting for a few other folks to show up, but let me know if you have any questions. Send me a chat message or jump in on the microphone if you'd like. And we are just starting our EIGRP design chapter here. All right. All right. A lot of times people ask me, what's a better routing protocol, EIGRP or OSPF? And oftentimes my answer is EIGRP, right? And there's a couple reasons why. Obviously, EIGRP up until last year, or 2013, was Cisco proprietary, and you could only run it on Cisco platforms. However, that's changed, right? As of 2013, it's been released as an IETF standard with some limitations, right? The stub routing features aren't available, and some other features in EIGRP aren't available, but basic functionality is still open and still controlled by Cisco, but it's been released as an open standard. The design elements in EIGRP make it much more tolerable to what we call arbitrary topologies. It's not nearly as complex as OSPF in regard to the hierarchy and the design elements of hierarchy that we would see in something like an OSPF network, right? What are you more familiar with working with? Are you more familiar with working with EIGRP or OSPF?
Both, but larger scale, I did the
right.
It was very neutral. I know it was complicated for that. EIGRP has its own limitations as well.
It does. Yeah. Yeah. I mean, obviously, OSPF scales to a much larger environment, right? But in that scalability, we create additional complexity, right? There are a lot more design restrictions to OSPF that you wouldn't see with the EIGRP. But in any case, whether it's OSPF or EIGRP, if the network is not designed correctly, it's not going to function correctly, right? The nice thing about implementing EIGRP that we didn't see with OSPF, particularly as the network scales and as the network grows, is we don't have to completely redesign the network as we're adding additional components to EIGRP, because it is basically a flat network, right? The downside, though, is as the size of the network increases, the stability of the network can become more difficult to manage, right? And that's primarily because of what? What's the nature of the protocol, right? It is a distance vector protocol, right? EIGRP is a distance vector protocol, so it doesn't necessarily handle, it doesn't have complete visibility or a complete picture of the network like you might see with OSPF, right, with a link state protocol. So you might see longer convergence times. You might see instability in the the propagation of queries and how queries get sent to the rest of the network and so on. EIGRP is also limited in size, right? In OSPF, we can scale up to about 300 OSPF routers in a network. In EIGRP, you can only scale up to about 100 routers or so diameter, not density, but diameter in a network before you start to see some serious performance issues with EIGRP. So as you scale the network, you have to implement additional design elements that you normally wouldn't have to put into place to make sure that the network is stable and it's still responsive to topology changes and so on. How do we do that in OSPF? In OSPF, we have to impose those design elements at the very early stages of implementation, because it's a very hierarchical design structure, right? You have your backbone area, you have your non-backbone areas, and you have different summarizations that occur on the ABRs or your ASBRs that are connecting different autonomous systems or different areas in the network, all right? The similarity, I guess, in a design approach would be, okay, in EIGRP, everything is in a flat network. Implementing a similar design architecture in OSPF would mean what? Putting everything in area 0, right? One area. It works okay, but only up to a certain amount, right? So to scale EIGRP, what's one of the biggest things that we have to consider in the scalability of EIGRP? Any ideas? Stub routing is an important concept, but I'm actually looking for summarization, right? Unlike OSPF, where we can only summarize on specific types of routers, right? You can only summarize on an ABR, you can only summarize on an ASBR. In EIGRP, you can summarize at any point in the network. It's because summarization is completed or configured at the interface level, not at an area border router under the OSPF configuration, right? So that's how we get that structured hierarchy in EIGRP, by creating these summarization points to reduce the size of our routing database, reduce the impact of topology changes across the domain, route changes, algorithm dual running or whatever, because we have these strategically placed summarization points in the network, right? The other point that you mentioned, of course, is the propagation of queries, right? And that's the other significant stability and convergence issue that we see with EIGRP, is the propagation of an EIGRP query. When do those occur? Right. Right, but so when does a query actually occur, though, specifically? There are certain scenarios where the algorithm doesn't have to run and a query isn't generated versus when a query is generated. Do you remember what that is? If there's a if a route fails or if I lose a route, but there's a caveat to that, right? The caveat is I don't have a feasible successor, right? That's when a query gets generated. If I lose a route, if I have a backup route and that backup route is a feasible successor, no problem. I go ahead and implement that backup route. I don't have to send a query to my neighbors. It's only if EIGRP does not have a feasible successor is when that query gets generated. And that query then basically tells the router, hey, I don't have a route to this destination anymore. Don't route through me, number one. And by the way, do you have another route, right? Do you have a viable route or an alternative route that I can use? And then we have to wait for those replies. But there's a domino effect, right? Because I send a query to my neighbors. If my neighbors have no information, they send a query to their neighbors. and so on and so forth. And then there's that 3-minute window in which we have to receive a response. If I don't receive a response within a 3-minute window, then I go into what we call stuck inactive. You mentioned that, right? Stuck inactive meaning that, well, now I don't have a route and I don't have anybody telling me that there is an alternate route, so I don't know what to do, right? So then we send an additional stuck inactive query. In the past, what would happen? If we went stuck inactive, what would the router do? And I can't remember the specific code version that this changed, but Cisco changed this behavior. But in the past, what would I do if I went stuck inactive? Remember?
I completely forgot. I remember.
So here's what would happen. It was pretty aggressive. It was a pretty aggressive approach to getting stuck inactive. What would happen is I'd reset the neighbor relationship, right? So not only now would I lose my route, I lose all my routes from that neighbor. Now we don't do that, right? Now the router, if it gets stuck inactive, which means a query was sent and I haven't gotten a response within 3 minutes, I go stuck inactive. I send a second query called the stuck inactive query, and that, as long as that stuck inactive query I get a response to that SIA, then I won't reset that neighbor relationship. And hopefully by the time it gets to the point where the neighbor's not responding, that neighbor relationship will get reset and then everybody can converge. But all that takes time, right? Queries can flood through all the routers in the network. That's going to obviously increase my convergence time. So, yeah, go ahead.
So we can actually do the variance, right? We can do the
yes.
4, right? And then there's the 1694, right?
Right. With IPv4, there's four paths. Well, EIGRP doesn't do unequal cost load balancing by default, right? It has a variance of 1, right? And we can adjust that. But keep in mind that still doesn't have anything to do with losing my successor, because variance, whether I'm applying a variance to my routes or not, as long as those routes fall within that variance threshold, and as long as they meet the feasibility condition, they're used as a successor. We're talking about what happens if the feasible successor fails. Now, I know where you're going with that, right? Because you're saying, well, okay, if one of those routes within that range fails, I still have additional successors because they fall within that variance range, right? And that's another way you can design in failover, right? Not to say, okay, let's just use equal cost load balancing. Let's go ahead and say this circuit path and this circuit path are equal, even though their metrics might be slightly different, so that I don't even have to send a query at all. I just lose one of my paths, but I still have another active successor because it fell within that variance scope. Does that make sense? Yeah. So keep in mind, variance is only applicable if the path that's part of that, that falls within that scope meets the feasibility condition, right? So even if my variance is 10, let's say, and my successor has a metric of 5, that means that anything from 5 to 50 would be considered equal. But we still have to meet that feasibility condition. If the reported distance of that path is still higher than the feasible distance of my primary path, even though it might fall within the variance, it's still not going to be used as an alternate path. Right. We'll probably see that again a little bit later on. All right. So we know queries can flood through many of the routers in the network, which is going to increase our convergence time. In order to change that effect or change that behavior, we'll implement summarization points in our EIGRP network. We'll implement stub routing features. We'll do route filters. We'll do to filter out query propagation. And the whole point, of course, is to minimize our convergence time, right? Now, we're going to look at some examples in this lesson and throughout this module. It's going to be focused primarily on IPv4, but just like with OSPF, EIGRP, ISIS, the IPv6 concepts are exactly the same, right? the principles are the same, the algorithms are the same, the math is the same. So it's, even though the implementation might be slightly different, the point of, and I'll point out what those differences are as we kind of go through the lesson, but the overall concepts are identical. All right? Yes. Yeah, we will definitely be talking about named EIGRP and using address families and whatnot. All right? Now, one of the topics that we didn't spend a whole lot of time talking about in the CCNP class is the sub-second convergence concepts, right? Now, we talked about the algorithm, dual diffuse update algorithm, or the diffusing update algorithm, and how that utilizes features like successor, feasible successor, and so on. In fact, let me show you what I'm talking about here, right? So you might have, for example, why is it not letting me draw here? Oh. Let me see here. Let's say I have a router here, all right, and I've got a path this way and a path this way and a path this way, and network X is what I'm trying to get to. And this is from the perspective of router 1. Now, and I'm kind of reviewing a little bit about the algorithm itself and what the concept of feasibility condition is, and feasible distance and successor and feasible successor and so on. So let's say this path here has a feasible distance of 100, and this bottom path here has a feasible distance of 200, right? So this path would become my successor because its overall metric is less than the bottom path. Make sense? But in order to create this fast convergence scenario, one of the key factors is the presence or the absence of a feasible successor. Now, by definition, what is a feasible successor in EIGRP? It's a backup route that takes over in the event that the successor route fails, but only if it meets the feasibility condition, right? And the feasibility condition states this: the feasible distance, sorry, the reported distance of the feasible successor has to be less than the feasible distance of the successor. Let me erase that and try that again. So, drawing this little diagram here again. Here's network X. So we already said that the feasible distance of this path is equal to 100, right? And we already said the feasible distance of the bottom path is equal to 200. But it's this distance from here to here, that distance that gets compared against this value. This could be 110. The overall path metric is still 200, but the distance from the neighbor to the same destination is 110. This path does not meet that feasibility condition, which means that if the primary path fails, switch my pen color back, if the primary path fails, I have to send a query, see if that backup path is still available, etc. So I'm not going to achieve faster convergence in that scenario. So as a network engineer, one of the things that I can do is I can manipulate metric values to ensure that the feasibility condition is being met on that backup path. So if the primary path fails, then we use the backup path immediately. Does that make sense? All right. So if there isn't a feasible successor, we know that EIGRP is going to send a query to its peers. It's going to have to wait for responses. Those queries slow down convergence times, et cetera, et cetera. All right? So we have to design the network properly. Now, we can manipulate metric values along the path as long as we know the impact of that manipulation, right? So for example, if I knew, for example, that this path here, switch my ink color here, this path here, I'm going to go up this way because I don't have enough, I don't know why my whiteboard thing is not working, but we'll just do this way. So I know that this path is 100, like I said, this path is 200. I may not want to change that whole concept, right? But I may want to change the metric from here to here so that that bottom path meets the feasibility condition. Maybe I still only want this top path to be used as a primary path. I don't want to load balance. I don't want to force traffic to use the bottom path. But I do know, because I'm a little smarter than a distance vector routing protocol, that this path is a unique path and it's not part of my original path. So I might say, okay, instead of this being 110, I want to make this 90. And the overall path metric might go down to 180. It'll still be the secondary path, but now I've forced EIGRP to look at that secondary path as a feasible successor, right? So if the primary path fails, the backup path is immediately used without minimal convergence time, right? There's still a little bit of convergence time, obviously, but we don't have to run the query process. We don't have to worry about queries being sent out, right? What is another method that can help limit the scope of queries and kind of indirectly speed up our convergence time? This is a little bit more challenging to do, but it is another option that you have, all right? And that's route summarization. Because if I'm summarizing routes, what is and this works in OSPF as well, we're going to see this in OSPF as well, what is the general impact of doing route summarization? Right. Routing table sizes get reduced, that's great, and that's a benefit, especially with a distance vector routing protocol. But also, if a route within the summary range, let me draw a diagram here. So let's say I have, a bunch of networks behind these routers here. As long as these networks A, B, and C are contiguous, as long as they fall within a summarizable range. I don't know if that's a word, but I made it a word. All right. As long as I'm sending those summaries, sending that summary into this router here. Oops, sorry about that. As long as I'm sending that summary into this router here, if network A goes down, the summary doesn't change, does it? All right. Well, there is a possibility it could change because there is a metric for a summary. How is the metric for all summary routes calculated, whether it's OSPF or EIGRP?
So there's the external routes, there's the summary. Summary is 5 to the EIGRP.
You're talking about administrative distance, right? I'm talking about a metric. So if I have 20 routes within a summary, and this applies to both OSPF and EIGRP, the cup is always half full with regard to metric, meaning that those 5 networks that are being summarized might all have unique metrics. Maybe one costs 65, maybe one costs 80, maybe one costs 150, whatever. I'm talking about OSPF costs. The summary metric is always the best metric of all the routes that are included in the summary. That's how summary metric is calculated. So if A happened to have the best metric in this case, we'll call it 100, and B is 200 and C is 300, the summary is going to have a metric of 100 unless A goes away. So the only thing that might change in the summary is the metric itself. The summary route will still be the same. Does that make sense? Well, we can apply a seed metric by doing route maps and applying some sort of policy-based routing. But I'm telling you that the summary doesn't necessarily change, right? If, let's just say this is a /16 that represents, you know, a bunch of networks behind here, a bunch of networks behind here, and a bunch of networks behind here. This is a /16, it's still going to be a /16. Even if all the networks behind router A go away, because those networks behind router B are there, and because the networks behind router C are there, the summary is still the same. The route itself is still the same. The metric might change, but the route itself is still the same, all right? You know, how do we use this to achieve faster convergence? Well, quite frankly, with summaries, we achieve it by simply not having to converge. Because just because a couple of the routes in the summary go away, the summary route doesn't change, so there's nothing to converge. Does that make sense? Right? Now, that means we're routing packets that will eventually get dropped. They may not get dropped right at the source, wherever I'm trying to route from. They'll get dropped further down the line, but, you know, there's a trade-off. Do I want to route a few packets that are going to get dropped later on down the line, or do I want to have to try and reconverge my network and send out queries and try to identify paths and not have summaries implemented? Does that make sense? Okay. Yeah. So you mentioned something, and I want to kind of clarify a few things. You mentioned a 5, right? That's the administrative distance locally on the local router for a summary for EIGRP. And we'll pull up GNS3. I'll throw up a config, and I'll show you that later on. But an EIGRP route, a summary route, once it gets advertised to neighbors, it becomes a standard EIGRP route. It's going to have an administrative distance of 90, right? So it's going to look just like a regular EIGRP route. It doesn't even look like a redistributed route. It won't have a DEX next to it. It'll just have a D next to it. But on the local router itself, which is interesting because the summary route is actually a connected route on the local router. It's connected to what interface? Null zero interface, right. So in the local routing table, the summary route will show up as a null zero route. But in the EIGRP topology table, you'll see the summary route in there with an administrative distance of 5, right? But when it gets advertised, it becomes 90 and a regular D route. So the connected null zero route, of course, is more trusted than the EIGRP summary route because the connected route has an administrative distance of 0. The EIGRP summary route has an administrative distance of 5. So the connected null zero route goes into the routing table. All right. But anyway, that's different than a metric. Yeah. And I know you know that. I just want to be clear that when we're talking about the metric for summaries, because a lot of people aren't aware of this, even though they might have gone through their CCNP and they've learned this in the past. If I have 100 routes in a summary, the summary route has to have a metric. The metric of the summary route is whatever the best metric is of all the routes in the summary, right? So what could change potentially if a route goes down within the summary range is the metric for the summary route. The route itself won't change, but the metric might change.
But why the summary? Why the summary is taking the shortest path, and the summary is tweaked by people?
It's not taking the shortest path. It's just assuming the metric of the best route. You know, it's and this is it's built into the protocol. I mean, there may be a mathematical principle for that. I always say, well, it's always summaries are always the cup is half full type of route, right? You know, saying, okay, out of all the paths in the summary, this is the best metric, so I'm going to make sure that my summary has that. To me, it makes more sense to say the summary route should have the worst metric because that's your worst case scenario, right? If I have 100 routes and 50 of those routes have a metric of 10 and 50 of those routes have a metric of 20, then I'm going to put a metric of 20 on the summary because that's my worst case scenario. It's just not the way it works. You know.
Different than the past, with that BGP, and you will advertise the summary and more specific routes or addresses. It will take the more specific ones and make more summary addresses.
Right.
So when manipulate the path of BGP, when you advertise the summary and specific routes, it will take the specific routes and we'll skip the summary because when you have more specific routes, it will take that and then the summary will be a backup.
Right. Well, and that's the same. It's the same with IGP protocols, right? In any routing, no matter what the routing is, longest prefix is used, right? So any route that has the longest prefix is going to be preferred over routes that have a shorter prefix. So summary routes would always be used last, but the summary route matches a null-zero interface on the local router. So you hope it's the last one used because then otherwise all your packets would get dropped. They wouldn't match some more specific routes. We'll play around with that a little bit later on, but and it's we're kind of spending a little bit of time on it, but it's not really that important. But just remember that even though we got off on this tangent because we were talking about how we could use summaries to achieve faster conversion, we know that we shrink the size of the routing table, check, that makes sense. That speeds up CPU operations, that changes whether or not we have to run the algorithm if a route goes down and so on. But those effects are pretty minimal. The effect of CPU operation on convergence, much less significant than the presence or absence of a feasible successor, for example. So we tend to focus more on making sure that there's a feasible successor in our routing domain, so that we don't have to send queries and so on. We can do that by implementing, well, in any event, whether we're doing equal cost or unequal cost load balancing, the feasibility condition still applies in either case, right? So we talked about that previously, right? The parameters for EIGRP, particularly for the metric, right? You're familiar with the EIGRP metric, right? We use, bandwidth and delay are the two primary parameters that we use. We have K values, K1, K2, K3, K4, and K5. K1 and K3 are the only ones that are actually used. They have a default value of 1, right? And K1 and K3 are directly related to bandwidth and delay, right? And then we have K2, K4, and K5. Now we can tune EIGRP metrics using the delay parameter if we want to. We can tune it using the bandwidth parameter. But if you adjust the delay on links, adjusting the delay or even adjusting bandwidth to a certain extent, but adjusting the delay on links, it gets really difficult to do that at scale, right? It's very easy to do when you're talking about single links between a couple of routers, but when you start to get into hundreds of routers on the network and dealing with feasibility condition from one router to the next, to the next, to the next, to the next, all of a sudden it becomes a lot more difficult, right? We don't typically adjust delay parameters. Bandwidth parameters. We tend to adjust the delay parameter because it's a little bit easier to work with and a little bit more predictable, right? But it's not necessarily an easy thing to do at scale, right? Especially in an EIGRP domain, right? Yeah. You can use route maps to do route manipulation. You can also use offset lists, right? And manipulate path selection using offsets. But typically we will focus on route maps and whatnot. We'll take a look at that stuff a little bit later on, right? Right. offset lists allow us to manipulate how metrics are presented to neighbors and how metrics are seen by from our neighbors, right? So we can influence the actual metric values. Sorry, my shoe is acting up here. So yeah, well, I don't know if we get too much into offset lists. I've used offset lists quite often when we're trying to manipulate path selection. But offset lists only affect the metric. They don't affect reported distance, right? So we still can't manipulate things like feasibility condition with offset lists. Well, not directly anyway. If it's downstream, we could, but not upstream, right? So it's kind of difficult to put an exact boundary on the number of EIGRP neighbors that a router can support. It depends on what kind of summarization you're using, if you're doing any route filtering, if you're doing stub routing. And this is something that they would typically ask you on the test. If you're doing an EIGRP design properly, then you're looking at about 500 peers. But if the network is designed poorly, if you're not doing summarization, if you have a lot of instability, then 20 peers would be your limitation. So there's a pretty significant difference there, right? Anyway. If we're implementing EIGRP with multiple autonomous systems, we can use this approach for scalability as well, right? Because we reduce the EIGRP queries by limiting them to a specific autonomous system, but there are also obviously issues that are related to running multiple autonomous systems. Remember, if I have routes coming from one autonomous system to another, they're going to be redistributed routes. Since redistribution occurs automatically between two EIGRP autonomous systems, but instead of having D routes, we'll have DEX routes, and then we may have issues with suboptimal routing because of administrative distance. DX routes have an administrative distance of 170. D routes have an administrative distance of 90, so we could see some issues there and so on. In this particular diagram that you're seeing on the screen, we're doing routes redistribution from RIP into autonomous system number 200 through router C. And then we have, well, router A is redistributes into AS100, router B, well, let me see here. So we've got router A here and router B here that are a member of both autonomous systems, right? Now, when the routes come in from RIP, how are they going to show up in AS200? They're going to show up as DEX routes, right, with administrative distance of 170, right? That's what the standard AD is for these redistributed routes. In AS100, of course, the internal routes there will have an administrative distance of 90, and as those routes get redistributed, so we've got the RIP routes come in here as 170 DEX, they're going to go into AS100 as 170 DEX, right? Is there a problem? Well, certainly internal routes are going to be preferred over external routes, right, because of the AD values. But the problem is that we may, router A may be a better path or router B may be a better path to reach those RIP routes. We don't know, right? Leaving this autonomous system, should I go to router A or should I go to router B? There's no way to really know this because of the administrative distance. It's the same, right? Router A redistributes those RIP routes into AS100. Router B hears about those route prefixes and advertisements from both AS200 and AS100, but they have the same administrative distance. They're both external routes to both autonomous systems. Whether it's AS100 or 200, they're external routes. So the route that gets installed in the topology database first is the one that ends up going in the routing table first, right? Which may not be an optimal path selection. The diagram's not that great to kind of specifically identify what they're trying to demonstrate here, but you get the general idea, right? We could have suboptimal routing taking place because of how the routes are being injected into the autonomous system, right? Here we see, so if router C sends, in this case, an EIGRP query to router A, all right, router A needs to query its neighbors. Well, router B is one of the neighbors, right? So router A sends a reply back to router C because it has no other neighbors in AS200, but it does have a neighbor in AS100. So it's going to query its neighbor in AS100 for the missing routes. So, and then of course those routers themselves are going to have to query their neighbors as well. All right. Why would this take place? Why would a query even take place in this case? Yeah, we lost a route. You know, router C lost a route. Maybe it lost a route. Certainly, it's not going to do a query for any route that would come from the RIP domain, right? Because those are going to get installed in router C as RIP routes. RIP routes have an administrative distance of 120. External EIGRP routes have an administrative distance of 170 and so on. But if I send a query to router A, we know router A is going to respond pretty quickly to router C because they're directly, well, they're neighbors within the same autonomous system. So the query from router C gets answered pretty quickly by router A. But router A still needs to wait for a response from its query that it sent into AS100 as well, because the queries don't stop at the autonomous system, right? I get a query in AS200, I'm going to send that query over to router B in AS100 because I'm a member of both autonomous systems. Make sense? All right. The point that I'm trying to make, I guess, and the point that they're trying to make with this particular slide is this last point right here, which is the query is not stopped because I move from one autonomous system to another. It's just delayed, but it doesn't get stopped. All right. The issue with this, by delaying that query, we're simply delaying our convergence time. We're not really effectively designing in efficiency into the design of EIGRP. We need to have summarization. We need to have stub routing features, distribution lists, route filtering, whatever it might be, to limit the scope of those queries. All right, either directly or indirectly from identifying whether or not a route needs to be relearned or whatever. Okay, so if EIGRP queries are not going to be stopped by creating these multiple autonomous systems, what would be the need then to have multiple autonomous systems? All right. There are actually several reasons that we might use multiple EIGRP autonomous systems. Again, not because necessarily that we're trying to limit the scope of the queries, right? What about migrating after a merger or acquisition, right? We have two companies, we put those two companies merge, or one company acquires another company. So in the process of bringing those companies together, we have two different autonomous systems. That's a short-term thing, right? Ultimately, we would want to implement one large autonomous system or one network, one converged network, but that might be a scenario. What about different authentication or different administrators for different groups, right? Maybe it's not necessarily a merger of two companies, but maybe it's and I saw this when I was working at NASA, you have an extranet, right? You're partnering with another company, you want to share some routes with that other company, but you don't want them to be part of your autonomous system, right? So they might still run their own autonomous system, you might run your own autonomous system. Those networks are under complete different administrative control, but there's some exchange of knowledge and information between those networks, right? As opposed to just doing basic redistribution between two completely different routing domains, right? The last and probably the least one that would be used would be to set up, I wouldn't say it's necessarily the same or a similar design as OSPF, but to kind of try and get that hierarchical design that you get with OSPF where you have multiple areas. So in this case, instead of having multiple areas, we have multiple autonomous systems, and we create hard summarization boundaries between the autonomous systems. When we're applying redistribution, we apply filters to redistribution as opposed to just applying filters to neighbor relationships. We can actually apply a filter to the redistribution process by using route maps and prefix lists or whatever we want to use to filter out routes that are shared between neighbors or between different autonomous systems. It's not very common, quite frankly. It's not very common. The biggest thing that we consider when we're looking at multiple autonomous systems is that it's primarily a stopgap measure. It's a temporary thing. It's not a permanent thing. Okay? So have you ever run into a scenario where you've had multiple autonomous systems before?
Related to different routing protocols
Right. Not two EIGRP ASs, but OSPF into EIGRP or BGP into EIGRP or whatever. Yeah, absolutely. We've got a little bit of time left, another 8 or 9 minutes or so before we actually take our first break. So I'm going to keep going here, but let me know if you need to take a break, but we'll be taking a break soon. All right. Now, this is another concept that we didn't spend a whole lot of time talking about in the CCNP class. It's called bidirectional forwarding detection. In fact, it's not covered at all in CCNP. It's a concept that's very heavily covered when you talk about things like BGP, but BFD is actually used in a lot of different routing protocols. Obviously, we know that when it comes to network convergence, the goal is to decrease the amount of time it takes for convergence to occur, right? The speed where a device on the network detects a failure, reacts to that failure, either internally by using its own internal calculation or by talking to peers and exchanging information with peers. How long does it take before I respond to a change in the network? That's convergence, right? And the goal is to speed up that process as much as possible so that the network recovers from topology changes and network changes quickly, right? The problem is routing protocols tend to talk at what layer? Layer 3, right? And in a lot of physical topology designs, the layer 2 design doesn't necessarily mean that there's an immediate layer 3 failure. Frame relay is a perfect example of this, right? In frame relay, the physical layer, the data link layer, the network layer are kind of separate from each other. Yeah, we still have, they're all integrated. I want to suggest that layer 3 can work without layer 2 working. But it's possible for a PDC in the cloud to fail or some routing issue in the cloud without having a physical layer failure or a data link layer failure on the local side of the router. Does that make sense? Because you've got a physical circuit path You've got a physical circuit that allows you to connect from the router to your carrier, and then you've got a virtual circuit path within the cloud that allows you to connect one router to the other, right? So layer 2 failure detection depends on the physical media. And layer 3 might not work, even though layer 2 might appear to be working, if that makes sense, right? What do we typically have to wait for in those scenarios? Well, how does a router, let's say I have I'll draw a little diagram here. Let's say I have a router here connected to a frame relay cloud, connected to a router on the other side, and then we've got this PVC that connects these two together, right? Well, let's say something fails in the cloud. Is there a physical layer or a data link layer failure on either side of these links? The answer is no, right? Yeah, the PVC might go down, right? But from the router's perspective, the physical layer's up, the connection to the service provider's up. So how do those routers detect whether or not there's a failure? They don't until the dead timer expires. The hello timer, the dead timer. So we don't have, that completely slows down the convergence process, right? The routers don't even know that they're not neighbors anymore until their dead timer expires. Because the hellos aren't being passed back and forth across the PVC, right? PVC is not responsive. So the layer 2 failures might be hidden from the routers, I guess is my point, right? Frame relay is a layer 2 protocol. So if there's no physical layer failure here and here, a data link layer failure here is kind of hidden from the routing protocol itself. So the only way that we can ensure that we fail over to a backup link or fail over to an alternate path is through the dead neighbor detection facility that's employed through the use of hello protocol, the hello packets, and the dead timer, 5 and 15 seconds for EIGRP, right? Every 5 seconds we're setting hello. If I don't get a hello within 15 seconds, I consider the neighbor down, and I delete the routes that are coming from that particular neighbor. Well, 15 seconds is a long time to wait for convergence, okay? So, BFD, this bidirectional forwarding detection, provides fast failure detection times for all encapsulation types, all media types, all topologies, and it decreases that failure detection time from possibly 15 seconds, even 60 seconds in some cases, if they're really slow speed serial links, to about 50 milliseconds, around 50 milliseconds. Think of it as like a heartbeat, right? What BFD does is it verifies connectivity between two systems. The BFD packets themselves are always sent as unicast packets to our BFD peers. And then those are actually UDP datagrams using, what the heck is the port number? For BFD. I think it's 3784. Don't quote me on that, but I'm pretty sure that that's the right port number, port 3784. I'll look it up later. If I don't tell you a different one later, that means that was the right one. But so what happens is in EIGRP, EIGRP informs the BFD process of the IP address of the neighbor that it needs to monitor. So this is obviously something that's going to have to be configured. It's not done dynamically. BFD does not discover its peers dynamically. It relies on a configuration that you apply as the engineer as part of the routing protocol configuration to tell it which IP address to use and which peer relationship to form for this BFD process. Have you ever heard of BFD before? Yeah. Have you?
Yeah, hey Scott, we use it in AWS. We use it for redundancy across 2 virtual CSR routers. We use a BFD, so if there's a CSR that's active and it uses BFD with the standby CSR, if it fails to receive, I guess, that heartbeat, it'll think it's down and then it'll send an API call to make itself be active. So we use it in AWS and Azure.
And with which routing protocol specifically? EIGRP?
EIGRP.
Yeah. Okay, excellent. So BFD on each router forms something called a BFD control packet. These packets are sent at a minimum of every 1 second. So in 1 second intervals until there's a BFD session established between the 2 routers. Okay. After the remote router receives that BFD control packet, there's what we call a session initiation phase. That's that initial step where the routers are trying to establish that relationship, that BFD relationship. It creates there's a bit that gets set in the BFD packet. It's called the I hear you bit. Basically, it's just a bit that gets set in subsequent BFD packets that says, hey, I know you're a BFD router. You're trying to establish this BFD session with me. Guess what? I know that you're there. I've now recognized that you're there, and you know that now because I set this bit, this I hear you bit. That's called the H bit technically, but the I hear you bit for all of those BFD control packets that get sent back and forth. Once both routers see that discriminator in each other's control packets, that means at that point that the BFD session is actually established between the 2 routers. Okay. And in every 1 second, they send those BFD packets until they see that discriminator value. All right. Once the session is established, then we negotiate timers. The timers are something that there's default timers. I'm not sure what the default timers is. No, it's in milliseconds. Yeah. It's like 50 millisecond intervals, I think, is the default. But again, I'd have to look that one up. But once the session is established, then they can negotiate those timers if it's configured on one side or the other. And those timers are negotiated asynchronously as well, meaning that they don't have to be identical in order for the session to be established. Once that's done, then we send out those control packets every 50 milliseconds. That's pretty much the limit to BFD. So that's why our convergence time is at least about 50 milliseconds in the event of a failure anyway. All right. So as long as each peer or each BFD peer receives those BFD control packets within that detect timer period, whether it's 50 milliseconds, 150 milliseconds, or whatever, that session remains up. The routing protocol works. The BFD maintains the adjacency and everything, and everything's copacetic. If I don't receive that control packet within that detection interval, call it a dead timer, I guess. I mean, that's basically what it is. It tells the routing protocol that the session failed, and then the neighbor determines the response, whether it's, try to kill that session or kill that neighbor relationship and reconverge and try and connect to another neighbor, choose an alternate routing path, whatever it is. What Aaron was describing is essentially the process, right? Could be just a failover event, switch over to a different router, switch over to a different path. Does that make sense? So that's interesting. I didn't know that you guys were actually making use of that.
Yeah, we have to buy the extended feature set just to use it.
Yep. Exactly.
But I think there's talks of them including it into their standard package, which would be a lot cheaper for us.
Yeah. And by the way, it's still not part of the it's still not part of the open standard version of EIGRP, right? That's one of the restricted features in the open standard version of EIGRP. All right. All right. So we will. So traditionally, when a network device restarts, all the peers that are associated with that device will detect that that device has gone down, and all the routes from that peer get removed. Makes sense, right? When the session is reestablished, well, the session gets reestablished when all the devices restart. They come up, the interfaces come up, the processes come up, and so on. Now, that transition from going down to coming up, that's going to result in the removal and the reconvergence or reinsertion of different routes, which then, of course, can start to cause kind of a domino effect, and it can spread across multiple routing domains. Hold on one second. So, have you guys heard of SSO or ISSU? Right. SSO, stateful switchover, or ISSU, which is the in-service software upgrade option that you have if you have multiple route processors, right? So, well, when we have a dual processor system and it supports that stateful switchover or that in-service software upgrade feature, we can continue to forward routing traffic while we're restarting the control plane on one of the two processes, whichever one we're rebooting, and the route removal and insertion doesn't occur in this case, right? Because one of the processors, one of the active processors or primary processors, is performing all those routing functions while the secondary processor is being upgraded or is restarting or whatever, right? So how does that actually work? Yeah, for stateful switchover or even in-service software upgrades. Yeah, well, generally speaking, the mechanism, yeah, right. So we have two separate route processors if they're both active, right? Information is being cached between one route processor and the other route processor. Stateful information is being shared between those route processors. So if one fails, the other route processor can take over those routing functions or whatever it might be. But all that state information is being maintained, right? This whole
Not aware of how the data information layer 2 or predictive layer. If that's sort of different.
Well, it's logically being maintained, right? That information is being exchanged between the route processors through a network. We used to have a physical layer connection, right, that would allow us, like a stateful cable that would allow us to transfer information, but that's not the case in most route processors. Because think about it, you've got a chassis-based system with different blades. Each blade is a separate route processor, so that information is being exchanged between those blades through the backplane or whatever of the chassis, right? Another feature, it's called GR, which is Graceful Restart, right? Is a nonstop forwarding feature as well. And when we have this GR feature implemented, what it does is it suppresses routing changes on peers during a switchover event. So if we're in the middle of an ISSU event or a stateful switchover event, we reduce the downtime of routing information, we reduce the negative effect or instability effect that we have with changes in topologies by simply allowing that graceful restart period to suppress routing changes on different peers during that during that downtime. All right. The other thing that Graceful Restart allows for is the forwarding of data packets to continue along known routing paths while the routing protocol information is being restored during the failover event, whatever that failover event might be. Typically, it's going to be a switchover from one processor to the other. The peer networking devices get informed via protocol extensions that the SSO-capable router's ability to perform Graceful Restart is an option through those protocol extensions. So each route processor, each device knows that it's capable of performing that Graceful Restart function so that it can understand that messaging that occurs between the two different devices for the Graceful Restart function. All right. So what happens? Hold on. These guys are. So when Graceful Restart is used, peer networking devices get informed about their ability to support this Graceful Restart function through these protocol extensions in the event that the SSO-capable routers need to use that feature. All right. Both peer devices have to have the ability to understand that messaging, that protocol extension messaging. So when a switchover occurs, the peer will actually continue to forward to the switching over router based on the Graceful Restart process for each particular routing protocol. Remember, this is not something that is specific to EIGRP. It's available with BGP, it's available with OSPF, ISIS, even LDP with MPLS. All these standards define this Graceful Restart interoperability that's available. All right. What's the ultimate goal of this GR concept, though? The ultimate goal is to provide a grace period for reestablishing neighbor relationships, routing relationships, and during that grace period, we're kind of suppressing changes, right? We're suppressing the, we're still forwarding routing information and using the routes that existed previously, but we're suppressing changes to, or any additional changes to routing information during that Graceful Restart period. That Graceful Restart period that's going to allow the reestablishment of neighbor adjacencies. Does that make sense? All right. Well, it's the goal of this is to suppress changes during that grace period, right? So that we're saying, okay, we're in this grace period now. Where we're doing an ISSU or there's some sort of stateful switchover event, there has to be a time period to allow those adjacencies to be reformed or that route processor to boot up and take its role. So during that period, we're not going to allow these changes to the topology or changes in the routing information. Right. That makes sense? Okay. All right. Now, we know that EIGRP is a flat design, right? It doesn't have areas like OSPF. And because it doesn't have areas, there are kind of these virtual ways to create a hierarchy in EIGRP as opposed to physical ways. Now, it's very similar to what we see in OSPF, right? Because in OSPF, we have multi-area design. We have our backbone area, which interconnects all of our non-backbone areas. And then we have routers specifically designated as ABRs, area border routers, from one area to the other. And what do we typically do on those ABRs? Route summarization, right. Well, isn't that really the biggest benefit to creating areas in OSPF? Limit the propagation of LSAs between areas, by creating these summary boundaries, right? Well, we basically do the same thing in EIGRP. Even though we're not doing it using an area design per se, we create these virtual areas through this summarization design. And that's what this diagram is describing here, right? EIGRP doesn't have an imposed limit like OSPF does, though. In OSPF, you can't have area 0 connected to area 1, connected to area 2, connected to area 3, connected to area 4, right? Those would be discontiguous areas. You'd have to have every area in OSPF connected to the backbone area by design, right? Unless you're using virtual links, but that's supposed to be a temporary or a stopgap measure, right? So unlike OSPF, you couldn't do something like this in OSPF, where maybe this is potentially area 0, this is area 1, this is area 2, this is area 3, or whatever. With EIGRP, we don't have that limit because we're not really creating areas, right? We're just creating boundaries of summary routes. So you can do summaries on these downstream links, you can do additional summaries on these links, et cetera, et cetera. Does that make sense? All right. Now, that being said, these are logically called zones, right? You can see the dotted orange lines represent these zones. Now, it's not something we physically configure in EIGRP. There's not a configuration that says, make this a zone, make this a zone, right? But a zone is a logical concept that represents something called a failure domain, right? Link and device failures have little impact outside of that circle or that zone. Does that make sense? So it's not something that we physically define. It's something that we're logically creating by creating these summarization boundaries and so on. A choke point, you can see the choke points are represented by the blue circle there, or the blue lines. That's where, choke points are essentially where zones interconnect, right? Physical links that allow us to go from one zone of influence to another zone of influence. This is where route aggregation occurs through the use of summarization. Reachability and topology information is exchanged at these choke points and so on. So anytime you see a circle here, here, and here, those circles represent my summarization links, right? So I'm going to be summarizing maybe in both directions, up or down here, up or down here, up or down here, up or down here, up or down here. All right? What's the key here, though? Right? The other thing we might do at those points, we might do maybe some traffic policies, aggregation of QoS policies, whatever it might be. But what's the overall idea? Right? You see the different layers. So in a layer design, in OSPF, there's 2 layers, right? Your backbone and your non-backbone, right? Well, it's the same concept here. Maybe this is layer 1, layer 2, and layer 3. Maybe these are my branch offices, this is my WAN, this is my core, whatever it might be. There's no specific definition of what these layers represent, but you get the idea. The idea is that we're trying to decrease the impact of topology changes across the entire enterprise by introducing points in the network where we can apply aggregation, summarization, policies, aggregate policies, whatever it might be. Okay? So when we're designing an EIGRP network, the main question that we have to ask ourselves to start with is how many layers do we need? And it's going to be totally dependent upon the scale of your network and how routes are being propagated through the network, how sites are interconnected, and so on. All right? At a minimum, you're probably going to have 2 layers. If you're following kind of a similar design concept as OSPF, where you have your backbone and you have your non-backbone areas. But typically, you're going to see 2 to 3 layers, right? Geographic dispersion might be one way of identifying where the layers might exist. The aggregation of routes might be how you define where the layers might exist. For example, this might be West Coast and East Coast operation. This might be the WAN. This might be my core, my data center, or whatever it might be. It's not really specifically defined in EIGRP. It really depends on what your overall network design looks like, or what the scope and the scale of your network looks like. The maximum number of hops from one side of the network to the other, we call that topology depth. I tend to call it the diameter, but it's could also identify how many layers you have, right? Ultimately, though, what's the goal? Ultimately, the goal is to make it easier to design how traffic flows through the network, make it easier to apply restriction policies, QoS policies, whatever it might be, right? When you look at this design, this overall design here, what is it that we're trying to accomplish? Two things. I get to pick on you. You're the only one here, so.
Not the operational functions and layering. The best way to layer the network, where you can actually just have multiple, you could have just multiple layers and separate them geographically.
Well, let's say it's just one autonomous system, right? Even though it's multiple layers, it's one autonomous system. Two things that we're always trying to achieve here, and that's the ultimate goal of any of these things that we talk about. You're already starting to kind of get the idea that with this class, it's kind of everything is high level, right? We're not getting into the fine points of these elements, but it's all about speed of convergence, trying to decrease the amount of time it takes for the network to self-heal or self-correct, and scalability. That's it. I mean, that's what any design is about, right? It's like in OSPF. The reason we implement areas so that we can do summarization, because we can only do summarization on area border routers. Well, summarization decreases the complexity of the database, right? Because we're decreasing the number of entries in our database, which increases convergence time, increases convergence efficiency, right, by decreasing convergence time and so on. So it's always about those two things. It's about scalability and it's about convergence, right? And that's ultimately what it boils down to. Okay? And obviously some of the things you mentioned are important, right? For example, integrating other autonomous systems, redistributing routes, whatever it might be, or integrating other networks, but again, it's still about scalability and convergence. When we're creating choke points, we need to adjust the topology, but we also need to consider the addressing in our network. That's a very important concept. The choke points themselves, and we saw this on the previous slide, these blue circles represent choke points. Well, what is one of the things that we do at those choke points? We summarize. And in order to do effective summarization, efficient summarization, what has to happen? You have to have contiguous address space. You have to have summarizable blocks of addresses, right? If you look at this example here, the choke points are positioned too low in the topology. In this particular case, we don't really have a whole lot of summarization options here. Yeah, we can perform, well, we've got 10.1.0 and 10.1.2, oops, right? 10.1.0 and 10.1.2 here, 10.1.1 and 10.1.3 here. Well, that causes a problem, doesn't it? Because ideally, I'd like to summarize to the 10.1 range, maybe do a /16 to the 10.1 range, or maybe do a /23 or 22 or whatever it might be, but I can't do that at this point because I don't have contiguous address space. The 10.1 blocks are separated, The 10.2 blocks are separated. So the subnets on these lower tiers are just, they're not contiguous, right? I mean, how could you possibly summarize 10.1.0.0 and 10.1.2.0 without including 10.1.1.0, right? You can't, right? So we can't do any summarization at that point. Obviously, a better design would be to make sure that we have contiguous address space, right? You know, or we move the choke point to a higher layer. In this particular case, we didn't change our address space. We created our choke point at this layer instead of at a lower tiered layer. That might work for us because maybe that's a good place to perform summarization. Maybe we're not concerned about just summarizing a couple of subnets on each of these lower tiers. We want to just summarize at a higher tier. And that's fine. In this case, we can do that because now we technically kind of have contiguous address space, right? Because we can just simply summarize 10.1, well, technically 10.0.0.0 with a slash what? What would we do in this case? They said a 10.1.0.0/22 and a 10.2.0.0/22. That would work, right? Because /22 would take me up to, well, that's a block of 4, right? Because that's a 252. And the third octet. 252 is a block of 4. So this would include, this guy here would include 10.1.0.0 to 10.1.3.0. And then that would include 10.2.0.0 to 10.2.3.0 with a /22. All right. Now, talking about this from a network architect standpoint or a design standpoint, you might say, well, let's not, for the sales folks or the marketing folks or whatever, let's not use 10.1.0 and 10.1.2, let's use 10.1.0 and 10.1.1 so that I can extend that choke point down to this point. Now, you look at that and say, well, okay, Scott, you're talking about going from 2 networks to 1 network. So potentially you're saving, what, 4 routes if you extend the choke point down to that second tier. But this is just an example. You have to kind of extrapolate this to potentially hundreds of routes or thousands of routes, not just 2 routes, right? Obviously, we can't put a whole bunch of routes on the diagram, but the concept is still the same. That makes sense. And that's what they're talking about here. All right? All right. So let's look at a basic 2-layer hierarchy, and then we'll take a look at a 3-layer hierarchy as well. In the 2-layer hierarchy, we have our core layer and our aggregation layer. Very similar to what we would see with like a OSPF design, where the core would be the backbone area and the aggregation points would be the ABRs attached to my non-backbone area. So very similar design in this case. The whole point of the core, as always, is what? High-speed routing. It lets you get your traffic from one topology area of the network to the other as quickly as possible. And that's what the backbone is designed for in OSPF, right? High-speed switching of packets. So we try to make the backbone as simple as possible. We don't overload it with policies, with applications of complex policies in the core. It's simply about getting reachability, right? So we don't even do necessarily aggregation in the core. We focus on the aggregation at the between that boundary between the core and the aggregation layer. In the case of of OSPF, this would be my backbone. It's kind of hard to draw it the same way with EIGRP, but we would have ABRs that would be performing this summarization from our access layer up to the core layer, all right? The core routers themselves, they should probably summarize routing information towards the aggregation layer, right? So just like you would expect to see in OSPF design, you would have routes being summarized from the backbone into the non-backbone areas, but you'd also have routes being summarized from the non-backbone areas into the backbone area. Same concept here, right? The fewer the routes that get advertised towards the edge of the network, the better, right? Because ultimately, in order to get from one edge component to another edge component, I'm going to have to go to the core anyway. So if I can summarize those routes that go down to the edge components, then the more efficient we'll be. All right. In the case of this particular diagram, we can actually apply policies, and that's what this policy line is supposed to represent. Policies on how routes get advertised and so on. The aggregation layer provides all of the user attachment points, right? So in this particular case, you can see that summarization is kind of being applied in upstream to the core. So I'm taking a bunch of routes or whatever networks that exist down at the attachment point, and I'm summarizing those routes up to the core. What about this policy, these dark blue arrows that are represented going back down to the attachment point, so the kind of the next layer? What do those represent? I'm talking about those two arrows right there that are going from the core down to that aggregation layer.
Oh, the routes, you mean routes, what kind of routes, right?
Yeah, what kind of routes are being pushed down, right? That's policy driven, right? You know, if I'm going to allow all the routes to be advertised or, you know, towards the edge, or only some of the routes to be advertised towards the edge, all right?
So the OSPF now with the access layer, would that be part of, so when you have like 4 buildings, you have to have a code, right? Because that's the by design, you have to have 4 with 3 buildings or more, right?
Right.
So how about these buildings when you assign them as codes? Would you put the ABR, you know, or have these folks part of the area zero, or have them outside the area? They should have their own areas, but I'm actually talking about the ABR. They be part of area zero.
They have to be part of area zero, right? Now, their physical placement would depend on the physical topology, of course, right? Would the ABRs be located in the buildings, or would they be located in the core building? Depends on the physical topology, how things are physically connected from one building to the other. But logically speaking, the ABRs have to be there, because that's the whole point of having that multi-area design. Yeah. That's, you know, you have to have an ABR in order to have a multi-area design, right? Well, we don't put links in an area, right? We put interfaces into an area, right? Yeah. So you're saying, okay, no, I get the question. I'm trying. So we're literally talking about 4 buildings, right? Out of those 4 buildings, which building would be? Is there going to be one building that's the core?
There's supposed to be one core,
right?
These are the rest of the folks, or at least, you know, the distribution layer somewhere in between, and you have the access layers, all this, right?
Yeah.
Or these layers, all these buildings, because, you know, I'm sorry, a couple of scenarios before, you know, some platform things, because when you have all these ABRs, and you should have them, of course, but I'm talking about interfaces that happen in area zero, and some mapping will be happening and will affect area zero and stuff like that.
depending on what is physically connected, right. And what's connecting the buildings and where those cables go to and so on. But I'm trying to think of the best way to answer that question. And I don't think there is an answer because it would depend on your physical topology. Would determine really where things would be physically located, right? I mean, would it really though? Because buildings would have to be physically connected somehow, right? Yeah. So, what are you trying to? What do you want me to answer? Like, where would the ABRs be located? You're talking about the three-layer model: access, distribution, core. Certainly, well, in regards to OSPF, and even it applies to kind of this scenario as well. The core is area 0, right? And in this case, it's my aggregation point for all my routes, right? Wherever that might be, because we don't have the areas here in this case. The distribution layer would be I think I get what you're getting at. Would the distribution layer really be, would it be routers, internal routers in the non-backbone area, right? That have all their interfaces in a non, in area 1 or area 2 or area 3? Or would it be the ABRs that have interfaces in area 0 and non-backbone areas? To me, it would be the ABRs. It would be the routers that have interfaces in the backbone as well as the non-backbone area. But then you have to look at, well, okay, are the ABRs servicing more than one area? Are they just connecting to area 0 and area 1? Or are they connecting to area 0, 1, 2, and 3, or whatever, right? Yeah. Yeah, so if you're doing multiple areas for ABR, then that makes more sense that that would be kind of a distribution point, right?
And then the ABR would be, the max would be 3 areas for ABR.
Mm-hmm. 3 areas per ABR, right? We'll get into that when we get into the OSPF discussion, but, all right. Where should we implement things like traffic acceptance, security policies, and so on in this design, right? Well, right here at the edge of the network. That's where all of my security access policies and my layer 2, my layer 3 traffic filters, whatever kind of filtering policy I'm applying should be applied there, all right? This is a 2-layer, so we kind of call this 2-layer model a collapsed core design, right? Where you have your core and your distribution layer kind of performing the same function, and then our access layer is separate. But in the case of a 3-layer design, it's very specifically defined, right? We have our core, we have our distribution, and we have our access. Just like the 2-layer design we saw on the last slide, the core layer's goal is to get traffic from one logical area of the network to another as quickly as possible. High-speed switching of packets, again, avoid the use of complex policies in the core, avoid the use of implementing QoS policies or security policies or whatnot. And then also avoid reachability and topology aggregation inside the core itself. The aggregation and reachability aggregation should have already occurred before the routes got to the core itself. So summarization occurs at the choke points between the distribution and the core layers, those links between the distribution and the core layers, and also between the distribution and the access layer. You can apply summarization as well, all right? We don't actually technically summarize inside the distribution layer itself, but between the different distribution layer routers, all right? Okay. Of course, the access layer, we know that's going to provide access for the users. We have our traffic policies, security policies, traffic acceptance policies. Any unwanted layer 2 or layer 3 traffic is going to get filtered here. And then if we do have routers at the access layer, particularly EIGRP routers at the access layer, make sure you configure those EIGRP routers as stubs, right? Because they're not going to be, there's no downstream routers necessarily that are going to be servicing routes up to the distribution layer or the core layer from those access layer routers, all right? From the logical design perspective, this 3-layer design concept, the distribution layer is my blocking layer or my blocking point for queries going from the core to the access layer. There's really no reason that queries need to go down to the access layer, so that's why we'd apply stub routing features to the access layer and apply the query blocking features to the distribution layer. Queries should only occur between the distribution and the core layer, right? Because that's where all the route aggregation takes place, and all the routing information takes place. All right.
But then we have the route access design. That's the access layer kind of, unless you're Summarization, so those not actually. But you know, route access design is different.
Right.
You're talking just about the multi-layer.
Right, the 3-layer design model. Yeah. All right. So you can see here that we're doing route policy at the distribution layer. In the previous slide, in the 2-layer model, route policy was implemented at the core. And route policy is not security necessarily for the end users. It's just how we're distributing routes from the core to the distribution. But here, route policy is done at the distribution layer. No route policy applied at the core layer. And all my traffic aggregation, well, really kind of occurs between here and here, right? Between the distribution layer routers and the core layer routers. All right. Hub and spoke networks, often applied, especially if we're connecting multiple branches to like a headquarters office or whatever it might be. The spoke routers, which are my branch routers, they're going to communicate to other spokes through the hub. All right. And this is traditional GRE tunneling and GRE VPN until we get into multi-point VPN and DMVPN phase 3 and different versions of DMVPN where we have spoke-to-spoke communication. Traditionally, it was a hub and spoke design, right? The hub is the aggregation point, really the aggregation for all the reachability and topology information for the network. All right, so naturally speaking, that would be really where the choke point should be implemented, right? And keep in mind when they talk about choke points, particularly on the exam, when you guys see references to choke points on the test, just think of a summarization point, a point where you're doing route aggregation or aggregating routes to downstream or upstream routers from that point, all right? The hub is really the only point in this case through which the spokes can reach other networks that are connected to other spokes, right? So as you can see from the diagram here, we're only going to advertise a default route from the hub to the spokes because the only way that the spokes get to other routes in the topology is through the hub, right? Keep in mind, in this case, we're not going to see any kind of spoke-to-spoke communication. This is not a partial mesh. It's not a full mesh. It is literally and physically just hub and spoke, all right? The spoke routes themselves should be summarized up to the hub towards the core. Makes sense, right? Which means that contiguous address space and addressing design is very important in this case, all right? with those point-to-point links that are connected between the hubs and the spokes, maybe use a /31 subnet to even conserve address space in that particular case. The addresses on the links, on those links should come out of the address space that's available on the spoke to continue to allow for additional summarization, right? So in this case, the 10.1.0.0/31 subnet is used to connect the spoke router on the left to the hub router, but we're also using the 10.1.1 subnet and the 10.1.2 subnet, which kind of falls in that same range. So we can maybe summarize to 10.1.0.0/22 or something like that for this group of networks, and that's what we see here. Because the 10.1.0.0/22 is going to include network 0, 1, 2, and 3. All right. We can even go smaller. We can go to a /23 if we only have network, say, 0 and 1. All right. Let's see. If you can't use /31s here, or you can't include on the link a network that's part of the summary or part of the subnets that are part of the spoke, then maybe use distribute lists or filters to filter subnets from being advertised back to the core that are not necessary. Right. All right. All right. Now, obviously, with route summarization, there is the possibility that you could create black holes in routing. And that is something that you definitely have to consider, right? Let's take a look at an example where we see a black hole being created, right? First of all, let's do a little bit of background on summary routes. We know that the overall objective of a summary route is to aggregate or to advertise 1 or 2 or 3 or a smaller subset of routes that represent a larger number of routes, right? So, for example, the summary has a shorter prefix, maybe a /16 instead of a /24, but it represents a whole bunch of routes, right? We know that, okay? The second thing that you need to be aware of is that when you do create a summary, on the router that the summary is created on, a null zero route is always created that matches the summary, right? So let's say, for example, I'm summarizing routes. Well, I'll draw a diagram here. Their diagram is okay, but it's not great. Let's say, for example, in this case, let me go back. I've got, you know, a whole bunch of networks behind this router, and I'm going to summarize all those to a /16. Well, I'm going to configure that summary on this interface, and I'm going to send that summary down to that router. Well, automatically, there's going to be a null zero route created on this router for that /16 summary. All right? Now, the idea is that, well, what's the purpose of that null zero route? Ultimately, what's the purpose of a null zero route? Why is it created? Right. It's a loop avoidance mechanism, right? The null zero route is a less specific route than the routes that it represents that are part of that summary, right? I didn't say that very well, but let's say I have 10/24 subnets, and I want to summarize those 10/24 subnets. I can't just summarize those 10/24 subnets. I have to summarize a block of 16, right? Well, ultimately, that means that there are going to be networks in that summary that the router doesn't own or the router doesn't know about, okay? So in order to prevent packets from matching a default route or being routed in some fashion that aren't supposed to be routed, we create this null zero route, which is a bit bucket for packets that don't match more specific routes that are part of that summary, okay? So the 10/24s, they're going to get matched to their appropriate packets because the /24s are more specific than the null 0/16. That make sense? But let's say out of those 10 subnets, maybe subnet 11 or subnet 12 in that block of 16 doesn't exist in the routing table. It's going to match the null 0 route because it's still part of that summary route. Does that make sense? Okay. So in a hub and spoke network, typically we have dual hubs to provide for redundancy, right? So if one hub fails, we want to be able to route to the other hub. These dual home networks are great for redundancy. If this router goes down, this router goes down, then obviously I want to be able to route this way, okay? But dual home networks create additional design challenges. They create additional things that we need to consider. So let's say, for example, in this case, when I'm summarizing spoke networks towards the core from a pair of hub routers, both the hub routers advertise the /22 summary. So imagine, if you will, that there is actually another network connected to this, the core of our enterprise, right? Well, the /22 is being sent up by both of these routers, okay? They didn't draw this very well, but I'll put a little cloud in there, all right? Now, this 192.168.0.0/22, sure, that represents 1, 2, and 3, because technically /22, that's a 252 in the third octet, so that's going to be a block of 4 networks, right? Network 0, network 1, network 2, and network 3. So far, so good. So the summary is being created on this link and this link going up to, we'll just call it the core of the network. All right? But both router A and router B are advertising those summaries. Okay? Because they're both advertising the summary, they're also both creating the null 0 route that matches that summary. Right? And by the way, particularly if this is EIGRP, does that summarization occur automatically, or does that summarization occur statically? Statically, right. And even automatic network summarization, which EIGRP used to do, doesn't happen anymore, right? Auto summary is not something that we have enabled by default. So a summary in EIGRP is something that's statically configured, which means that that null 0 route basically always exists. All right? Now here's the problem. If router A loses connectivity to maybe a physical layer failure here, to a downstream route. So now all of a sudden the 2.0 network, which was advertised up to router A using EIGRP as a /24, that /24 route disappears from router A. Now all of a sudden packets going to router A for /24, what's going to happen to them? That /24 route doesn't exist anymore. But the /22 does, as a null 0 route. So the /24 packets are going to end up matching the /22 null 0 route, and those packets are going to get dropped, right? Right. There has to be some kind of redundancy between the routers. We'll see that in a little bit, but yeah, that's kind of the point, right? That's where this idea of a black hole occurs. Even though technically I should know that the /24 no longer exists, because I'm sending the /22 up to the core, the connection to the core didn't fail. The summary is a static summary, the null 0 route's still going to exist. That makes sense? All right? Because the summary is still being advertised. All right? By the way, that null 0 route is called a discard route because packets that match the null 0 interface get dropped. They go to a bit bucket. All right? Now, how do we prevent that from occurring? How do we prevent that process from occurring? We have to connect these routers together so that this /24 route can be advertised here, and then it can be advertised over to here. So if I lose this route through this path, I can send the packet down through the other hub router. Now you hopefully, in that they are connected to the core, that we shouldn't be exchanging routes through that core, but it's not drawn that way in this particular case. All right? Yeah. Right. It's still all part of the same network, right? We're not trying to connect to two different networks. But there is a downside, right? If we connect to two hub routers, rerouting traffic from one hub to the other, great, no problem, right? As long as the hub routers are advertising the networks to each other. But we have to be careful not to configure summarization between the hub routers also, because the discard route, that null zero route, gets installed with an AD of 5, but the other routes that we learned from the other routers have a higher AD, so they're not going to go into the routing table. Right? All right. All right. The other issue that you can run into is something called suboptimal routing. And suboptimal routing means that we're just simply not taking the best path to reach a particular destination. If we connect these hub routers together, to prevent the concern that we talked about in the last slide, we connect these routers together. That's great for failover. It's great for connectivity, but then we might introduce suboptimal routing. All right. Let's say, for example, that our topology is a little bit more complicated, right? We've got a couple of networks, network hanging off of router A, 10110, that needs to be advertised, a network hanging off of router B, 10120, that needs to be advertised. So a default route to the spokes, to the spoke routers is not the best option here, right? We still want to summarize all the routes advertised from the hub to the spoke as much as possible to reduce the routing overhead. But again, by doing this, we might create suboptimal routing. You can see, for example, the 10.1.0.0/16 network, which comes from the core, is being advertised down to the spoke router. Now we're getting our more specific routes, 10.1.1.0/24 and 10.1.2.0/24, but what is what's the potential that we see here with the suboptimal routing? All right. Well, let's break it down. Okay. The hub and the core networks easily summarized, and we can see that summary listed here as 10.1.0.0/16. So that's very easily summarized, and that summarized route is being advertised down to the dual-homed spoke routers. Well, the dual-home spoke router in this case. So that's the purple route that we see there. All right. The packets that go to 10.1.1.0, they're forwarded directly up to hub A. Makes sense. But they can also go up to hub B, can't they? Because of this 10.1.0.0/16 route, we can send the packets up to hub B, or we can send the packets up to hub A. All right. Now, the yellow routes that we see here are routes that are leaked into these links from the hub routers. It's a feature called route leaking, and we'll see some details a little bit later on. And basically, it's just a way of distributing more specific routes over a particular link, because the more specific routes are going to be more preferred than the more generic routes, right? So we're leaking more specific routes through the summary. We still get to summarize all the core networks, 10.1.0.0/16, on the hub routers, but we leak the more specific routes through the summary so that we can essentially identify a better path for those more specific routes. All right. I don't know if I described that very well, but I think you get the general idea. Right. Right. And later on, we'll see some configuration examples of that. Okay, setting up route leak maps and so on. All right. Where can the suboptimal routing come into play? Well, the diagrams in this is all Cisco's courseware here. Not that great, but what we're not seeing here is metrics applied to these links, why one path might be decided. Let's say the routes are not being leaked, right? We're not leaking in the 10.1.1.0/24, the 10.1.2.0/24. Well, now router C is going to have to make a decision. Do I go up to router A for 10.1.0.0/16, or do I go to router B for 10.1.0.0/16? And that would be dependent upon what kind of links these are and what kind of metrics are tied to those particular links. Okay. Now, we're not saying that it would be suboptimal to go from here to here to here, and we can't say that technically because we don't know what those links look like. I don't know if the link between C and B is better than the link between C and A and so on. Maybe this is a 10 meg link and maybe these are 100 meg links. So this would be an optimal path. It's hard to say. So the diagram doesn't really give us the idea, but if all these links were the same, or, geez, let me just say, well, yeah. I was going to say, let's say that this is a 10 meg link and this is a 100 meg link. That would still make this a more preferred path, possibly. Because metrics would still be involved. Well, not with the summary, they wouldn't, of course. Summary would just have one metric for all of the routes. They should have had a better diagram. It's not a great diagram. Hello. All right. EIGRP scalability in a hub and spoke environment relies on a couple of different factors, right? When the spokes are connected to the hub, if they're connected to the hub over multiple interfaces, the processor itself is the primary limiting factor. That would be like a point-to-multipoint topology or a kind of a multi-point topology. But when you have point-to-multipoint topologies over a single interface, what's the limiting factor? If I'm using multiple interfaces, CPU is the limiting factor. If I'm using a single point-to-multipoint topology over a single interface, what's the limiting factor? Congestion on the link. Queue congestion, right? EIGRP has an actual theoretical limit to the number of peers that it can have over an interface, and that's 4,000 peers per interface. As long as they are in the same network prefix, right? And we can see that listed here on the slide. It's actually, they said 3,000. It's actually technically 4,000. Yeah, it's much higher. It's much lower in OSPF because OSPF is much more processor intensive, right? The databases are much larger and so on. All right, link state information. All right. If EIGRP is used in production environments, if we have, say, over 800 EIGRP neighbors, well, what you're seeing in this diagram here, all right, let me see, how can I describe this? If I have, okay, I know how to do this. All right. So if I'm using EIGRP in a production environment where I have over 800 or more EIGRP neighbors from a particular interface point, any topology that has over 1,400 neighbors, what I'm trying to describe, they did a case study. That's what this slide is trying to describe here. They did a case study that you can see what they used in this test environment. They dual homed NPE G1 with 1 gig of memory, 3,000 prefixes advertised to each spoke. And what they were trying to identify was the convergence time based on the number of neighbors. As you can see here, they went from, minimal number of neighbors all the way up to over 1,000 neighbors. And we saw the time in minutes without a stub configuration exponentially increased for convergence. I'm trying to, the slide doesn't really tell us much about how, what this scenario was. And I'm trying to just see how I should describe that. We understand, all right, let's break it down bullet point by bullet point, right? They're saying here that EIGRP hub and spoke scalability relies on several factors. Number one, configure the spokes as stubs. All right, great. What would that accomplish? If I'm configuring in a traditional hub and spoke environment the spokes as stubs, what does that do for me? It prevents queries from being sent from the hub to the spokes, number one. It also allows me to identify or limit the amount of information that the spokes are sharing with the hub as well, right? Whether you're doing connected, summary, receive only, whatever it might be. So it's limiting the amount of information that's being distributed from the spoke to the hubs, as well as limiting the query process to the spokes. So they mentioned both of those in this bullet point here. The first one is here, the one I just circled. The second one is here, minimizing advertisements to the spokes. How do I minimize advertisements to the spokes from the hub using a stub feature? I can't, right? Because when I configure a spoke router as a stub, where is the limit of information flow applied? From the spoke to the hub, not from the hub to the spoke.
So summary is, of course, internal, right, at the spoke, right? Not going to receive other than summary or APR or, right?
When you configure an EIGRP router as a stub router, connected and summary are the only routes that it will advertise, not receive.
Right. Yeah.
That it will advertise to the upstream router, right? So configuring stub routing on a router does two things. It limits the amount of information that's being provided from that stub router to the non-stub router. And in the case of defaults, it's connected and summary, connected routes and summary routes that are part of EIGRP. And it also limits the queries, right? So the queries, the hub router won't query the spoke router, okay? Well, in OSPF, it depends, right? Because there's 4 different ways you can configure an area, right? You can do area stub, which means you'll get summary routes, but you won't get external routes, right? You can do totally stubby, which means you don't get anything except for default route and so on, all right? What I'm trying to figure out, and I'm not doing a very good job of it, but what I'm trying to figure out is how to describe this particular slide and what they were trying to represent. Now, they had it looks like in this case, they had over 1,400 routers, or neighbors, right? The orange line is supposed to represent the number of neighbors. So it's clearly more than 1,000 neighbors. It looks like maybe 1,500, maybe 1,400 neighbors that were successfully configured, all right? But it looks like, okay, I get what they're trying to say here. I get what they're trying to say here. The orange line is supposed to represent the number of neighbors that you can support if you use the right design features, stub configuration, summaries, etc. In a non-stub configuration, you're limited to the number of neighbors significantly. So that's what this blue line represents here. The same deployment, same physical topology without the stub feature enabled, which means that you're limited to what, maybe 300 neighbors in this case. And convergence time increases significantly with the topology change as the number of neighbors goes up. Whereas convergence time here, this orange line, convergence time kind of flatlined, stayed the same, regardless of the number of neighbors you had, because you had those features implemented. Finally got there. Okay. All right. So I guess the point is, if you look at this diagram, that it really does demonstrate how much efficiency is gained by using summarization, stub features, and so on in an EIGRP design, particularly in a hub and spoke design. All right.
We usually do it connected static.
Connected and static. Yeah. So what connected and static means is that any connected route that's part of EIGRP, so it has to have a network statement or it has to be participating in EIGRP, and static routes that are redistributed into EIGRP, right? Yeah, through a distribution list and so on. Okay. Now, another key to this is not just the first bullet point. That's the stub configuration that we see here. That's the first bullet point, but the second bullet point as well. Minimize advertisements to spokes. How do we minimize the advertisements that go to the spokes? There's only two ways to do it. You either advertise a default route to the spoke, or you advertise some sort of aggregate or summary route to the spoke that represents all the core routes in the network. All right. That was a tough slide because they didn't really give us a whole lot of information on what that table was supposed to represent, but there we go. All right. Now, the other problem that you can have is that remote sites, spoke sites, can be dual homed with two routers on the remote end. Each of them is connected to the hub router. All right. So C and D in this case would kind of represent the remote sites, and then A and B would represent the hub routers. All right. So both spoke routers are configured as stub routers, which means that they're doing by default connected and summary. That's what they're advertising up to. They're advertising connected and summary up to the hub router. That's the default configuration for stub routing in EIGRP. If I go into a router and I say EIGRP stub, it's going to send up connected and summary routes. Okay? What's the problem with that? If the goal is to advertise the 10.1.1.0 subnet up to the hub, who's the one that's going to advertise it? Well, so this is an EIGRP router, this is an EIGRP router. This guy's configured as a stub, this guy's configured as a stub. D is going to advertise the 10.1.1.0 subnet. C is not. You guys agree with that? Why would C not?
So it depends on what is being configured.
Well, C is configured as a stub router.
Yeah.
And by default, in EIGRP, when a router is configured as a stub, it's only going to advertise connected and summary routes.
Right.
The 10.1.1.0 subnet is not connected to router C, which means router C is not going to advertise to 10.1.1.0 subnet. Right? So the only way, yeah, go ahead.
What if this fails, right? So there's cross on the other link. So with the other router,
Like this link fails? Yeah, then we wouldn't be able to reach the 10.1.1.0 subnet. Right. Now, the way to fix that is to create a summary here this way on router D for the 10.1.1.0 subnet, because this guy will advertise the summary back up to router A, right? Or change the stub configuration on router C, not to just advertise connected as summary, maybe advertise other routes, right? Sorry?
You can do the C, right? So stub receive. So what is the other?
There's 5 choices.
Yeah, exactly. Receive.
There's stub static, stub connected, stub redistributed, stub receive only. Receive only means I'm not going to send anything, right? Did I give them all? Connected, summary, static, redistributed, receive only. Yeah, those are the 5, right? Those are the 5 choices you have with stub features, right? Connected and summary are the defaults. In any case, in any of the 5 choices, though, it has to be part of EIGRP. So if I do stub static, excuse me, if I do stub static, it has to be static routes that are redistributed into EIGRP. It can't just be any static route. It has to be part of the EIGRP routing process, all right? So in this particular case, if the link between router B and D fails, what's going to happen? So we're not going to, again, these diagrams they're kind of crappy, but here's the core network. The core network's not going to be able to get to that destination because it's no longer being advertised because of the stub configuration of router C. We can see that it's doing connected and summary in this case. So router C is going to receive the 10.1.1.0 subnet from router D. So router C is going to know that the 10.1.1.0 subnet exists. But it's not going to advertise it to router A because it's configured as a stub router. They do not advertise learned routes. They only advertise connected and summary routes. All right?
So it depends on the environment, right? So if you have, when you have a hub and spoke, the spoke will only access that to the hub, right?
Say that one more time.
What kind of environment is this? Because when you have a hub and spoke, the spoke will advertise connected and static hub.
Connected and summary.
Connected and summary, sorry. Or static, you can do static as well.
Of course, yeah, you can do all 5 if you want. Well, you can't do all 5. Receive only is separate. But
C and D spokes.
C and D are spokes.
Okay, the C will be sending the summary in connected to
Correct.
another spoke.
Yes, C will send its connected and summary over to D, and D will send its connected and summary over to C.
Well, what kind of configuration is this? The spoke only sends to, you could, of course, with the tweaking, but the spoke will only send to the hub, right? In terms of summarization and connected routes.
This is a unique design in that they have 2 spoke routers for redundancy or whatever it might be, dual home spoke routers. So this is hub, this is a hub router, and these are my spokes. Okay, just an example.
Okay, so that's going to be happening at the interface.
Yes.
Right, so under the interface will do the summary.
Within the branch, right.
That's away from the stuff.
Correct. The summary still exists,
Yeah.
right? So I'm sending a summary up to here maybe it's not just a 10.1 subnet, maybe it's a whole bunch, and I'm sending a summary here, but that's done at the interface level, from the spoke to the hub, okay? All right. But because the 10.1.1.0 subnet's not connected to router C, even though router C is learning about it from D, it's not going to advertise it to A because of its stub configuration.
Because with this case, the spokes will configure each other. And that's against the whole design idea of having stuff.
No, stub, when a router is configured as a stub, it's a stub for everybody.
Right, but the interface, at that interface, because you're having this spoke router connecting to somewhere connected routers.
But remember, stub configuration in EIGRP is not at the interface level. It's at the router level.
But with that name, you're sending
Summary and connected.
Yeah, to the other spoke.
Correct.
I'm not sure if it's within the validated design. My idea is here that we spokes only send routes to the hub, right? And that's the idea of configuring.
I get what you're saying. Yeah, this is just an example to identify where you might be missing routes, right? So even though you look at this design, right? You look at this design and say, hey, we're perfect. We got redundant spokes. We got redundant connections to the hub. So even if this link goes down, everybody over here is still going to be able to get to this network. And that's not the case.
Right.
Because of the stub configuration of router C and router D. All right. So in this particular case, they're giving you an example of what could occur if this particular design was implemented. Does that make sense?
Yeah. And I was just trying to understand the whole design. By design, the spokes only speak to the top, right? And then
Correct.
Spokes.
Yeah. We would see a similar problem with the default route. If the default route's being advertised down, that default route's not going to get advertised to router D. So if this link goes down, router D is going to basically lose its default route. It's not going to be able to get to the core because router C is not going to advertise the default route because it's not connected and it's not summary. All right. All right. To establish this full design, this fully redundant design, we would have to do stub leaking. Yeah, stub leaking where we leak the 10.1.1.0 route out, still send connected in summary, but leak out the 10.1.1.0 subnet or leak the default route into the network. To the other spoke, right. From router C to router D.
Now that makes sense, more sense for me. Within the stub can do the leak. And then
right. And then you get that redundancy and whatnot. So we'll break for lunch now. After lunch, we'll go through the case study with DMVPN and EIGRP. That's the last thing we'll do with EIGRP. And then all right, so to wrap up the chapter on EIGRP, what we're going to do is take a look at how EIGRP operates in a DMVPN environment. And in this particular case, we're going to look at it from the perspective of a case study in which we kind of look at an example and take a look at a sample configuration and see how this applies in this sample configuration. EIGRP is actually the routing protocol of choice for a DMVPN network, right? We know that DMVPN has kind of migrated through several different phases, three major phases of configuration. We have DMVPN phase 1, we have DMVPN phase 2, and DMVPN phase 3. In DMVPN phase 1, we had really just a basic hub and spoke topology design. In DMVPN phase 2 and DMVPN phase 3, we kind of migrated from a basic hub and spoke topology to what we call a complex hub and spoke topology, or a full mesh topology, or a kind of a hybrid topology where we had the ability to have some spokes connected in a full mesh and some spokes connected in a hub and spoke environment. It doesn't really matter which version of DMVPN we're using, which phase of DMVPN we're using, or how complex our topology is. EIGRP routers will always establish adjacencies, neighbor adjacencies, in a hub and spoke manner. So even if we have that spoke-to-spoke communication, and we have the ability of allowing the spokes to communicate with each other directly, we're still going to see that EIGRP router establishment or adjacency establishment in a hub and spoke design. All right. Now, what this does is this allows us to reduce the total number of adjacencies really to a minimum amount, and which allows for much greater scalability and essentially reduces the spoke router hardware requirements, but still allows routing through optimal paths. All right. So we have less of a load on the spoke routers. The spoke routers don't have to be as powerful or as robust as, say, the hub router might be. Now, in this particular diagram, we're looking at a DMVPN phase 1 deployment, which only allows for a hub and spoke topology. The central hub and all the spokes that are connected to the central hub use what we call a multi-point GRE tunnel, or for short, MGRE. So on this side here, we've got a multi-point GRE tunnel. Oops, sorry about that. On this side here, we've got an MGRE tunnel, which is just simply a multi-GRE interface. The DMVPN relays multicast between the hubs and the spokes, so multicast is supported in this environment, and that means that automatic neighbor discovery as well as EIGRP adjacencies can be formed, because those adjacencies are established using a multicast protocol, 224.0.0.10 to be specific, or FF02:A if we're talking about IPv6. All right. All the spoke routers establish adjacencies with the hub router. And this is primarily because there's really no direct path between the spokes, and the spokes don't establish adjacencies with each other. Now, this is a simple design because it allows the spoke routers to be configured as stub routers. All of the adjacencies are focused to the hub. The hub provides all of the routing and all the routing configuration or routing advertisements to the spoke routers. In the diagram, spoke 3 router is going to advertise its connected network, which is the 192.168.30.0/24 subnet. The hub router then receives that advertisement, and then it places that route into its own routing table because it learned it from spoke 3. And then the hub, because it has an adjacency established with the spoke 2 router, also learns about the 20 subnet from the spoke 2 router. But there is a particular problem in that the 30 subnet that's learned from the spoke 3 router is not advertised to the spoke 2 router, and the 20 subnet that's learned from the spoke 2 router is not advertised to the spoke 3 router. Why is that? What is it about EIGRP that causes that to occur?
It's a split horizon.
Right. It's split horizon. Okay? Split horizon says I'm not going to advertise any network out of the same interface that I learn about it on. And because we're using a multi-point GRE tunnel interface, we're not using sub-interfaces or separate physical interfaces. Split horizon becomes a bit of a problem here. Okay? Now, to solve that problem, because we're terminating our our DMVPN endpoints on this multi-point GRE tunnel interface, it is a single interface on the hub router side, and because EIGRP is a distance vector routing protocol, it's going to obey the split horizon rule by default. So the hub router doesn't advertise any routes through the same interface that it receives them on. When we're using EIGRP to route through a DMVPN cloud, we always have to disable the split horizon on that hub router. And this applies to all DMVPN phases, by the way. Every DMVPN phase fundamentally operates the same way when we're establishing our initial topology. We always operate in a hub and spoke environment. Granted, in phase 2 and in phase 3, we have the capability of communicating from spoke to spoke, but that spoke to spoke communication is not permanent, it's temporary. So that hub and spoke topology is always required. So we remove split horizon by going into the multi-point GRE tunnel interface and putting in the command no IP split horizon EIGRP and the autonomous system number. Pretty straightforward. All right. Without that split horizon command, now we can route between the two spoke routers, the two networks, the 20 subnet and the 30 subnet, but that traffic still has to pass through the hub. DMVPN does not allow spoke-to-spoke multicast, so spokes, even if we're using phase 2 or phase 3, spoke-to-spoke multicast is never allowed, so the spokes can never establish a direct adjacency with each other. Even if you allow spoke-to-spoke communication, that's typically going to be unicast routed traffic from spoke to spoke, you're not going to be able to establish an adjacency between those routers. Now, we saw the establishment or the ability to establish multi-point GRE tunnels between the spoke routers when they were needed in DMVPN phase 2. So in phase 2, spoke-to-spoke communication was actually allowed. But spoke-to-spoke tunnels still do not relay multicast. So even if you have spoke-to-spoke EIGRP communication or any kind of spoke-to-spoke communication, spoke-to-spoke EIGRP adjacencies don't get established. All right? Again, this really allows us to reduce the total number of established adjacencies in our DMVPN mesh networks with a high number of spokes, and it allows us to use low-end routers in our branch offices because we don't have a high number of adjacencies in the spoke locations, only in the hub location. All of the spoke networks get advertised through the hub. So the hub kind of serves as the next hop for spoke-to-spoke communication. Now, you take a look at that and you go, okay, well, but DMVPN phase 2 and DMVPN phase 3 allow us to establish spoke-to-spoke tunnels for routed traffic. If the hub in a DMVPN environment with EIGRP, the hub is always acting as the hub, and the spokes can never establish adjacencies with each other, it makes it kind of pointless, really, to have any kind of spoke-to-spoke communication, right? Because the traffic, the next hop address for all traffic is going to have to go through the hub anyway, all right? Well, that's true by default, but it is possible to keep your hub and spoke topology but still use the full mesh capabilities of DMVPN to actually forward traffic through the network. So the hub router can still relay all the advertisements that it receives from the spokes, but it doesn't necessarily have to act or advertise itself as the next hop for those particular routes. The default behavior is for it to advertise itself as the next hop for those routes, but we can configure the hub to not do that, right? And this slide shows an example of that configuration. We actually have to go into the hub and configure the hub to advertise the network that it receives from the spokes, but it has to keep the spoke IP address as the next hop, as opposed to inserting itself as the next hop for those particular routes. All right. If we take a look at the spoke to routing table here, it receives the 30 subnet from the hub router, but it takes spoke 3's IP address as the next hop. And that's because we implemented this no IP next hop self command under the EIGRP configuration process for the DMVPN configuration. Does that make sense? So this allows us to take advantage of that spoke-to-spoke communication, because the next hop actually reflects the spoke router's IP address that the route was learned from. All right? So when we establish direct spoke-to-spoke traffic or direct spoke-to-spoke routing, that's going to be forwarded directly between the spokes. All right? So as a best practice standard, if I'm using DMVPN phase 2 or phase 3, I want to have this no next hop self command when I'm using EIGRP in those environments. Another thing to consider is where I apply summaries and how those summary addresses get deployed in the DMVPN environment. We know that if the number of DMVPN spokes go up, so do the number of advertised routes that are represented by those spoke routers. Now we can counter the total number of rising routes by using summarization. Since all of the routers are advertising their routes and they're being advertised through the hub, we can do all of the summarization on the hub. We still have the no next hop self command, so we can still ensure that specific routes are being learned, but summarization can be used. All right? In this particular case, if I tried to summarize, let's say that, for example, I summarize all of the LAN networks on the hub. So we did a IP summary dash address, EIGRP1. That's a standard summary address command. We would apply this to the multi-point GRE interface. And I said 192.168.0.0.255.255.0.0. So I'm summarizing every 192 network, every 192.168 network as a /16. What's going to happen in this case? Any ideas? All right. The hub is only going to advertise the summary networks to the spokes, but the hub is going to act as the next hop for that summarization. Now, summarization in this case helps us reduce the number of advertised routes, but now all that spoke-to-spoke traffic is flowing through the hub again, as opposed to going from spoke to spoke. So I guess the next question would be, is it possible to summarize all of the networks that are advertised by the spokes, but still allow for optimal routing through the DMVPN cloud? I'm guessing that that's probably going to be something that we can do. That's why we're bringing it up, right? Obviously. All right. Now, this is a specific solution that was introduced in DMVPN Phase 3. We already know that both DMVPN Phase 2 and DMVPN Phase 3 allow us to build a partial or full mesh with spoke-to-spoke communication as needed. But with DMVPN Phase 2 summarization, it's a trade-off. You can have the summarization through the hub, reducing the size of the routing tables, but then forcing all the traffic to pass through the hub, or you can simply do spoke-to-spoke routing with all of the individual routes. In DMVPN Phase 3, we can perform optimal full mesh routing and still maintain summarized EIGRP routing or summarized EIGRP advertising. All right? That's what we see in this slide. Well, this slide right here. Okay? I'll break this down, and hopefully it will make more sense as I kind of break down each of the pieces of this diagram here. There is a protocol that we use called the Next Hop Resolution Protocol, NHRP. It's part of DMVPN in all phases of DMVPN, and it allows us to identify, well, it's kind of in what we call, in DMVPN, in a DMVPN environment, we call it an intermediate routing protocol, all right? The whole point of NHRP is to improve the efficiency of whatever existing overlay routing protocol we might have, like EIGRP, like OSPF. And it's not that it was introduced in DMVPN Phase 3 or DMVPN Phase 2. It's been around from the beginning. But in Phase 3, there are enhancements and additional configurations in NHRP that allows the hub to issue what we call routing redirects to the spokes. Meaning that maybe the initial lookup or the initial routing lookup goes through the hub, but then the hub instructs the spoke to utilize a different next hop for that traffic flow or for that particular routed traffic. All right? Let's take a look at how that works based on this topology diagram here. The EIGRP configuration itself is very, very simple. The hub router peers with the spokes, just like we saw before. The split horizon rule is removed on the hub, so we have the no IP split horizon EIGRP. The hub advertises all the networks it receives from the spokes, starting, identifying itself essentially as the next hop. And then we do summarization on the hub to reduce the number of advertised routes. So far, so good, right? All the things we've been talking about are in play here. Let's say that a packet gets sent from the spoke 2 LAN and it's supposed to go to the spoke 3 LAN address. The spoke 2 router is going to look into its routing table and it's going to see that there's a summary network route that includes that destination network with the hub router as the next hop. The initial packet is then forwarded to the hub router, which then forwards it on to spoke 3. All right? Now that sounds very, very much like EIGRP with DMVPN Phase 2 without the no next hop self configuration. So the question then remains, why is Phase 3 better than Phase 2? Now the hub router has spoke 3 listed as the optimal next hop for the spoke 3 LAN 192.168.30.0. So when the hub router gets configured with the command that you see on the screen here, IP NHRP redirect, okay, the hub router sends an NHRP redirect message back to spoke 2, notifying the spoke 2 router that the packets that are supposed to go to the 30.0 subnet, which is the spoke 3 LAN, are better forwarded directly to the spoke 3 router. So even though that initial packet would go through the hub, subsequent packets would be sent directly from spoke to spoke, right? The spoke 3 router receives the NHRP redirect from the hub, and it gets configured with an IP NHRP shortcut, creates a new NHRP entry into its routing table. That entry basically just states that the Spoke 3 router is the next hop for the traffic that's destined for the Spoke 3 LAN subnet, and the traffic is forwarded then directly across the spoke-to-spoke tunnel to the Spoke 3 router. Does that make sense? All right. So you may not have been aware of those details with the various phases of DMVPN, and of course we talk about DMVPN a little bit in the CCNP class. We get into some of the changes and some of the differences in the different phases, but this helps us a little bit more to understand those design concepts that we're looking at. Scalability of EIGRP over a DMVPN network does depend on several different factors, right? What is the depth of the topology? How many peers do I have? What are the number of advertised prefixes that I have in my DMVPN environment? But more specifically, what phase of DMVPN am I running? Right? Because we know that we have efficiencies that are gained by implementing DMVPN phase 2 or phase 3. So what we're looking at here is kind of a chart that represents some labbed out. We saw this previously when we were talking about spoke routers and setting them up as stubs and whatnot. The EIGRP behavior that you're going to see depends on what version of DMVPN you're using, what phase of DMVPN you're using. We know that the newer phase is going to result in much lower convergence times, even if we're using the exact same EIGRP topology. Because we have the optimal routing function, but we also see the fastest convergence times with DMVPN phase 3. In a production environment, a practical maximum number of EIGRP peers that you would get to see in a DMVPN phase 2 network is around 600 routers. That's generally about what we saw when we looked at a single hub and dual hub deployment. You get above 600 routers, you can see that the convergence time kind of spikes a little bit. We're seeing that in this particular case. Yeah, we see a minor increase in convergence time as we go up to the 600 router point, but once we get to that 600 peers or 600 neighbor point, convergence times increase significantly. All right. All right. Scaling a DMVPN network beyond that number means that we usually have to have multiple hubs, and then each hub would terminate 600 spokes so that we can kind of load share or share that responsibility across multiple hubs. Now we also see at the bottom chart, there's a linear correlation between the number of prefixes that are advertised and convergence time. Now this is easier to combat, right? Because with prefixes, we simply implement summarization. And summarization can keep that prefix number down quite a bit. All right? And that would be the goal in that particular case, is to establish points where we can implement summarization to decrease the number of prefixes that might be advertised.
Would you hit throughput issues at your hub well before that 600 limit?
Most likely. It does really depend on your traffic patterns and your traffic flows and the speed of the links. you know, it's a hard thing to quantify because, you know, 600 peers or 600 neighbors with very slow speed frame relay circuits, maybe 256K or 64K or 512K links, you're not going to see as large of an impact as if they were, say, 1.5 megs, right? So it does depend on the speed and the bandwidth and so on. But yeah, in most modern environments, you would definitely see the bandwidth.
Yeah, because in our AWS deployments, we're running a DMVPN mesh over for our deployment for all of our clients, and our dual hubs are set up at, 2.5 gig for IPsec traffic, and all the hubs are limited at 10 meg. So we get requests for increases to the 10 meg licenses on the environment routers, but that's easily going to saturate our 2.5 gig hubs.
Exactly. And that's really what I was saying, right? It just depends on your physical architecture.
Right.
Right. So clearly in that case, that 600 neighbor limit would never be seen, right? You'd never be able to reach that point.
Right. I think the max is anywhere, I guess if everyone's using it, it's anywhere from 200 to 250 environments.
Exactly. Okay. So in this chapter, which was our EIGRP chapter, we talked about the ability to create these arbitrary topologies, a lot more flexibility than what we saw with OSPF. To increase the efficiency of EIGRP, we can use route summarization, route filters, we can limit EIGRP queries. Running multiple autonomous systems is not an effective scaling technique because it doesn't limit queries across the autonomous systems. We can use BFD to offer faster failure detection, and then Graceful Restart suppresses routing changes on peers while failover is occurring, while we're seeing stateful switchover or in-service upgrades. Zones allow us to kind of logically separate through these things called choke points. Choke points is where we apply our summarization techniques and so on, and multiple zones that are equally distant from the core form the layers of our network. And we saw that we had a two-layer hierarchical model that we could use, and we had a three-layer hierarchical model that we could use. We always summarize at the choke points, but we have to be aware of black holes created by those null-zero routes and how routes are being advertised, as well as suboptimal routing. And then we typically will employ the use of a two-layer or a three-layer topology. We're going to use stubs in our hub and spoke environments to decrease the amount of convergence time it takes. And for EIGRP for DMVPN, we support hub and spoke topologies, but we also offer optimal routing in a DMVPN phase 2 or a DMVPN phase 3 environment. And that is what we talked about. Later on, we'll try to take a look at some examples and get into some more of the configuration.